Hi, thank you for joining this webinar about what makes Capella different. I am Stéphane Bonnet from Thales, and I am in charge of MBSE coaching and community in all our business units. I've been the Capella Design Authority for almost 10 years now. In this webinar, I am not going to give a detailed presentation of all Capella features. That would take far more than 45 minutes. Instead, I'm going to try and explain the global philosophy driving Arcadia, the method, and Capella, the supporting workbench, using a few representative examples. So Capella is an open source solution for MBSE. In MBSE, we find systems engineering, but the same approaches would be valid as well for software or hardware architectural design. So Capella is different in many ways. It has been used in Thales in multiple domains: transportation, avionics, space, and outside Thales in domains like automotive and space as well. Capella is different in many ways. Its scope is very delimited. It is coupled with a method. It provides original engineering helpers that is the work of engineers every day. And it is also different in the way it is developed and made available. So in this webinar, I'm going to focus on some key differences about Capella. And the first of these differences is the scope. What is Capella meant for? There are 1,000 ways of performing model-based systems engineering, and Capella and Arcadia cover architectural design and a little bit more. So Arcadia is a method, and I will come back on that. And Capella is a tool supporting the method. The main target of Arcadia and Capella are not necessarily the modeling experts, but rather the engineers who usually use DOS, Visio, Excel, and so on. So the ultimate goal is not to have modeling experts sitting beside domain experts, but to have systems engineers embracing the cultural change of MBSE. So while architectural design is the main focus of Arcadia and Capella, we also touch a little bit of enterprise architecting with a slight overlap with some nav views, for example. We have a framework to manage non-functional properties. We can use Arcadia and Capella to anticipate V&V activities and so on. So the main objectives of the Arcadia method is first to better understand the customer need. Then to define and share the solution currently developed among all stakeholders. Then one very strong objective of Arcadia is to secure system, subsystem, software, hardware engineering, and prepare subcontracting. Capella can be used to early evaluate and justify architectural design against engineering specialties, and then to prepare and master V&V activities. So the second key difference of Capella is that it is method coupled. What does it mean? The essential of Arcadia, the method that is embedded, or which is the DNA of Capella, fits in an A3 page. A dedicated book will be published in December 2017, but before that, in a A3 page, you can find all the concepts that are used in Arcadia. The concepts are pretty common. There's nothing really new there, but their usage is precise in a focused framework. So on this page, you can see that there are two main focuses that are capturing the need and capturing the solution. And for each of them, we have in this slide a summary of the tasks, concepts, and objectives of each engineering perspectives. so the users can really use that as a guideline in their activities. So I said that there's a strong coupling between the method and the tool. On this slide, on the left side, I will have the method with different engineering perspectives, operational analysis dedicated to capturing how the system will be used, system need analysis, capturing what the system will do for the users, and then logical and physical architecture that provide an intermediate and finalized views of the solution that needs to be developed. So on the left side, there's the method. On the right side, there's a tool. So what we use in Capella is pretty close to SysML, but it has been simplified and enriched. So we're using functions, data flows, structures, interfaces, behavior. But because we have a very precise scope, which is architectural design, we've been able to simplify some of the concepts that of SysML that were not useful for our systems engineers. The focus in Capella is on ease of use, and that covers, for example, complexity management, and I will have demos on that, in particular for the management of instances and the management of functional analysis. And an example of a small thing that contributes to ease of use is, for example, colors. In Capella, every element that is related to functional analysis is green. Every element that is more related to the structure is blue, the components. And then every element that is part of interfaces is red. And in Thales, this contributes to a shared understanding between engineers of all domains. And then in Capella, we have the method explorer, the DNA of the tool. And this method explorer is a step-by-step guidance. It is a central interaction point of all Capella models. So the first thing we do when we start a project is to define modeling objectives, strategies, and guidelines that support this strategy. So basically, we don't model to model, but we model to help solve engineering problems. This is a big piece of work. It takes time and experience, and this is typically requiring mentoring or coaching. But with Arcadia and Capella, it's not a start from a blank page. There's a lot of experience and feedback that has been captured both in the method and the tool. The next key difference of Capella is a small one, and it's the operational analysis, something that we usually don't find in equivalent tools. So operational analysis is something that is often missing in our engineering activities. We believe we know what the customer wants, or we know how we operate the system, and we don't question the way we do things, even though we don't always know why they're done this way. So starting with why is one way to identify key topics and deliver a system that better matches the customer need. And to do so, we're going to use the operational analysis in Arcadia. So here we have in orange operational activities that are performed by operational entities. We don't have a box that represents the system in this engineering perspective. And we can model operational processes that are like highlights in this interaction diagram. Once we have identified and worked with the customer on this operational analysis, we can use it as an input for the system need level analysis, what the system has to perform for the end users to reach their objectives. So in Capella, there's a strong articulation between operational analysis and system need analysis. And a lot of traceability and automatic deductions are provided by the tool. The next key difference is comprehensiveness. Pretty often, MBSE is mainly about modeling the architecture from a structural point of view. We define blocks, we define interfaces, we define properties on these blocks, and we analyze how the architecture behaves. But there's more in architectural design. So functional analysis is a technique that is deeply anchored in the practices of systems engineers. And we've made strong effort to allow engineers to conduct functional analysis and structural modeling in parallel. And I'm going to show that in the next slide and in the next demo. And then MBSE is driving or contributing to a wide range of engineering activities. So integrating functional analysis, structure, and interfaces. One of the goals of Capella is to help identify and justify the interfaces between components with functional content. So on this slide, we see in green functions, in blue components, data or dependencies between these functions that are allocated to dependencies between the components. And the dependencies can be formalized using exchange item, data elements, and at the end of the process, we end up with interfaces defined on components and allocated to physical path. So this is a global approach, and I am going to illustrate that in a demo. So this is Capella. In green, you have the functions. In blue, you have the components. Between the functions, we have dependencies. They are named AC, CE, BD, and DE. So right now, these dependencies are just labels or names. But we can also define on these dependencies, we can formalize what is actually flowing, provided by A and required by C. And using the semantic browser of Capella, we can see that this AC element is actually carrying operation 1. The BD functional exchange is actually carrying event 1 and operation 2. And these these elements can be displayed in one diagram. So they are described with class diagrams, and they are related to the functional exchanges. In Capella, we have a way to display the exchange items on functional exchanges instead of just seeing the labels of the functional exchanges. So now I see that between A and C, I'm carrying operation 1. Between B and D, I'm carrying operation 2 and even 1. I can run a model validation on this functional analysis. And then I will realize that I have quite a few issues, including completeness issue. And some of these completeness issues are the fact that I need to make that a bit more clear. This functional exchange is actually carrying exchange items that are not provided by the source port or expected by the target port. If I check that, my semantic browser doesn't tell me that I am actually needing operation 1. So we can execute a quick fix, and then when I come and check this function port, I now see that it is carrying operation 1. I can repeat this operation for all similar errors. Okay. So now my functional analysis is over, and I can create links between components, or I can group the functional exchanges and start working on the interfaces between components. So between LC1 and LC2, I'm creating a functional exchange that I'm going to call 1, 2. And using the selection on elements, I'm going to allocate them to this component exchange. So that tells me that between LC1 and LC2, I have an interface that I've called 12 that carries the functional content of these functional exchanges. So here I did that manually, but I also can use what we call a modeling accelerator that is going to generate component exchanges automatically based on the functional exchanges that are already defined. So basically, it is to be considered as an initialization, and then there's some engineering work to group them differently and so on. So once I've done that, I have started working on my interfaces, and I can use another accelerator to actually generate the interfaces of LC2. So I'm going to use modeling accelerator, generate interfaces from allocated functions. This is done. And I'm going to display one specific diagram showing that. So now I have a diagram that shows all the interfaces that are provided or required by component LC2, and their content is justified with functional content. If I remove one of the elements in one given interface, so this is something that I change the content of this interface, I can perform a model validation on the component, and then the tool will tell me that, where is that? One form is, there's a missing exchange on this interface compared to functional content. And then I have two possible quick fixes. First one is to add the exchange item to this interface. The other one is to remove it from the functional exchange. So here I'm going to add it. So this was for the demo showing the global integration of functional analysis, structure, and interfaces. This has been shared with the SysML-v2 working group, who is also working right now in SysML for a better integration of functional analysis with the rest of structural and interfaces. So model-based systems engineering is about placing the models at the center of the engineering activities. So being model-based is not only drawing architecture diagrams, but it impacts most of the user engineering activities. And this is an important thing to consider when embracing MBSE. All the stakeholders are impacted, specialty engineers, V&V guys, managers, and so on. So this is an example where models are at the center of a team. So this is taken in one Thales business unit. And posters made of the model are shared in a corridor, and we can see in green the functions, in blue the components, the dependencies between them, interfaces near the bottom. And these dashboards also include extracted metrics for management. So this is just to mention that Arcadia and Capella are intended to support a comprehensive approach. So there are other important and addressed aspects of engineering that I'm not going to develop here because we don't have enough time, even though the first one is going to be developed a little bit. And there might be the topic of future webinars. So the first one is modes and states. Second one is how to drive V&V activities by functional content that is described in the model. And then how to relate architecture model to feature models and manage variability in the context of product line. And for that, we have a partnership with Pure Systems, who developed the tool Pure Variants. Still about comprehensiveness, another piece of big difference, architecture evaluation. So if we want to consider architecture model as a reference for other engineering activities, then they have to be able to integrate specialty engineering. Capella comes with a development environment for viewpoint development. So basically, when we create a new viewpoint, we extend the language, we manage new layers in diagram, we change graphical representations for these elements in diagrams, or we couple with other tools. So Capella Studio, which is open source, is dedicated to build autonomous viewpoints. On this example, it's something that is related to timing in sequence diagram. And then we have bidirectional coupling with specialty tools. We have several examples, including one with a coupling with the citrus simulation environment, or a coupling with Safety Architect, which is a tool from All4Tech. So I'm going to give examples of both, starting with the coupling between Capella and Safety Architect. So in Capella, we have data flow diagrams, and a viewpoint has been developed to add some concepts into Capella and manage a concept of failed event that can be attached to functions or function ports. And once failed event has been added in data flow diagrams, there can be there's a transition for Safety Architect, and what we see here on the diagram is actually initiated by the functions. And in Safety Architect, engineers will analyze the local failure conditions and create the barriers for these failure conditions. In Safety Architect, still, automated generation of fault trees, and the fault trees that are obtained in Safety Architect can then be reintroduced in Capella as critical functional chains. So this is an example of meaningful coupling between two tools, because it doesn't make sense to redo everything in Capella. Capella is intended to be the backbone of architecture models, not necessarily to cover all activities. The second example is an autonomous viewpoint that is a prototype at Thales, and it is a partial implementation of the Marte profile. So basically, this one is dedicated to performing parametric analysis on architecture. So we are able to capture hardware characteristics, and we can see that we have on this on the left side here the means to create specialized physical components like processors, IP blocks, buses, bridges, sensors. So it's a profile on top of Capella, and each of these come with their own properties. Then we are able to enrich model, like functional model with consumption information. And this add-on provides different dashboards for parametric dimensioning, estimations, and computations. Next key difference of Capella, it's engineering continuity. The goal is to ensure a continuous flow from system to subsystem, or from subsystem to software architecture or hardware architecture. So basically, the goal is to reduce the predominance of textual requirements between upstream and downstream engineering teams, and this is a pretty big challenge. So I showed previously the different engineering perspectives introduced by Arcadia, and at system level, we end up with a system physical architecture, so a detailed architecture that represents the system, how it is going to be developed or subcontracted. And for each of the elements of the system physical architecture, we will have to make choices between buying, making, subcontracting, and so on. Capella comes with an add-on that allows a seamless initialization, and it is iterative, to initialize a subsystem model based on the system model content. And this is something that I am going to illustrate. So this one is in a video, because my environment here on the macOS environment didn't have the system to subsystem transition. So we are here in the system, in the in-flight entertainment system, which is a reference model of Capella that you can download on the Capella website. And we're going to open the physical architecture of this in-flight entertainment and focus on one element that we want to subcontract. And this element is the passenger remote control that is here, that allows to control the movies. So we use a system to subsystem transition, and our goal is going to initialize the system need analysis of the subsystem. So we need to create a new subsystem model that we call remote control. And the tool is going to compute the context of this element. So this is coming. We select the remote control. We have several options, but here we just leave them by default. And once we do that, the tool computes a context and provide a list of the elements that are going to be added in the system need analysis of the subsystem. So we have a few functions, we have actors, and so on. So we accept everything. We now have a new subsystem model. We can see that in the Project Explorer view. And we're going to create a diagram in the subsystem model to represent what we have retrieved from the system level. So the system box now is called the passenger remote control. And I'm going to add all my actors. So I have the passenger and the private video display unit. So what is interesting here is that the passenger was a real actor, but the private video display unit was actually a component in my system level. And now it has become an actor because my system of interest has changed. So we retrieve all the functions of these elements. So the functions of the remote control, the functions of the passenger, and so on. So I'm just going to make a little bit of layout effort so that we can really understand what is actually happening. So it just takes a little bit of time. We're improving on this topic, but still we could always do better. And now that I have my architecture diagram at subsystem level, this is supposed to be considered as read-only, and then the downstream engineering team, the subsystem engineering team, would work on the logical and physical architecture of their subsystems. And now back to the system model, we're going to add a new function in this remote control, and we're going to add a new functional exchange from the passenger to the remote control. So we have changed the interfaces of the passenger remote control at system level, and we are going to propagate these changes to the downstream model, to the remote control model. So we use the same command. We use the same target project. We don't need to recreate one. And then the tool gives us a summary of the differences. So we have some differences in functions. We have a new function, a new functional exchange, new function ports that have been created, and so on. So we can analyze and accept or reject changes. Here we're going to accept all of them and see the impacts on the remote control subsystem. So I'm going to display the new function. So I'm using the all allocated function tool of the palette. And now I have the new function that has appeared in the remote control with the new functional exchange towards the passenger. And then the work of the engineer at this level would be to propagate that in the logical architecture and take that into account. So we can, the flow between system and subsystem is really greatly helped by the tool. Back to the slides. The next key difference is not really a technical one. It is the fact that Capella is open source. So what does this mean for you? First of all, a bit of history. The whole story started in Thales in 2016 when our management asked us to work on engineering transformation. And we've been working both on the method and the tool right from the beginning, involving practitioners right from the start. And during quite a long time, Arcadia and Capella have remained proprietary solutions, but we took the decision for multiple reasons in 2014 to make it open source. So we had multiple rationales. I'm not going to develop them, but it was quite a cultural change in a company like Thales. Since then, it has been a growing initiative. The adoption is better than what we anticipated. We have collaborative funded projects helping us. We have Capella Industry Consortium that has been created this year and that will define the future of Capella and the roadmaps and so on. So if ever you want to join the industry consortium, I invite you to contact us. On the Capella website, you can find a few case studies, including one from Ariane Group, working on avionics of launchers, one from Areva, a nuclear plant maker in France, and Continental Automotive. Of course, we have tons of examples in Thales as well. So what happened since the open sourcing of Capella a bit more than 2 years ago? New components have been developed. Both the method and the tool have evolved. And I will show that even though we came to the open source world, the roadmap of Capella is still under control. It is managed, and openness doesn't necessarily mean anarchy or chaos. The good thing about Capella is you can think of your own use case, your own evolution, your own contribution, and you can do that with us, and you can contribute to making the ecosystem grow. So all the elements that we see here, like the import of requirements, documentation generation, model querying tool, are features that have been added to Capella because we worked with between several organizations. If you want to adjust your Capella to your objectives and context, there are a lot of resources to do that. There are public APIs, forums, wikis, where you would find tutorials, development guides, and so on. And there's also commercial offers to help you go faster in this initiative. Next key difference of Capella, I've already said that we have involved the end users right from the start. And I want to really focus on one specific recent activity that clearly illustrates the philosophy behind Arcadia and Capella, which is don't put something in the tool if you don't know how it is going to be used. And this is about modes and states. In a system, the impacts of the possible combinations of modes and states are difficult to analyze today. We can have multiple levels of modes, like at system, subsystem, and then they combine with states and so on. And what we need is to study the variability of the system over time during its operation. And this is pretty complex. So in June 2015, we had an initial idea, which was to introduce the concept of system configurations that we found in the Marte specification, and relate this configuration to modes and states in order to study the different configurations. So we came with this concept in the tool. We developed a first prototype, and we were able for each configuration, so here it's a hybrid vehicle, we were able to specify which component, which function, which interface was present or not. And we were able to visualize the impact of these configurations on the diagram. So everything that is gray here means I am not available in this particular configuration. In July 2016, we realized that our pilot users had struggles with the engineering approach. They were not clear about what was a configuration with respect to a mode or a state, and if it was a real thing or just a technical element. So basically, they were struggling with what we gave them. So in August 2016, we've had a really productive brainstorm. And in this brainstorm, we actually came with what was a missing concept. And the missing concept was situations. So a situation is a combination of current modes or states in different modes or state machines. And once we use situations as a prism to analyze our system, we actually can achieve quite a lot of good results. So we use configuration to specify what is expected, like what comes with each mode or each state. We can also specify what is expected by the customer. We can build global computed configurations and so on. So it's something that is really well documented in a paper that we have published in the last INCOSE symposium in Australia in July. And this is also the result of a joint work between mainly Thales and Altran. Altran has worked on how to compile configuration. So we have a prototype that is available for public download. Don't hesitate to ask us. And next year, we're going to introduce or to integrate this add-on into the core of Capella, because we now consider that it is mature enough. And both the method and the tool matured together. So I said that Capella is user-driven. So I'm going to give some examples. So the development of Capella has always been driven by the end users. It has been specified by them, it is monitored by them, and we work with them continuously. So in the middle of the slide, you have the Capella development team, and they have multiple interfaces. On the top, they have the Thales internal interfaces, the Thales modeling community, some enabling components like Kit Alpha, diff merge, like key technological bricks that we need. Serious with OBO, and we have a need capture that is really well defined, so where we can retrieve all the evolution requests from each end user in all our business units. So we are able to feed the Capella development team with the Thales end users' needs. But we also have the collaborative projects, the industry consortium, and some funded evolutions that organizations have provided because they were lacking that or this feature in Capella. So we basically have a lot of input, and the Capella Industry Consortium is now responsible for the decisions about the changes and the definition of the roadmaps. The Capella development team works in agile mode. So what I'm showing here is something that we find on the Thales internal wiki. So it's not available publicly, at least not yet. And it is basically the fact that every end user can registrate and participate to the sprint demo that are performed by the development team. So every second week, users can attend the demo and see the current developments that are being made, and they can follow that the evolution that they requested is actually implemented as they thought it would be. And so this is something that is really interactive, and it really helps building the right products. So you don't have that right now outside Thales, but what you have is an access to the public, all the nightly builds, meaning that every morning you can test and comment using the forums any recently developed features before it is promoted in an official version. There's a warning though: do not deploy this development version operationally because they are not fully validated. But you also have access to what is currently being developed, and you can try to influence or make comments or suggestions on these developments. So Capella is driven by end users. What does it mean concretely? First of all, it means that we ended up with original solutions for complexity management. And I'm going to perform a demo on that right now. And we also ended up with productivity tools, such as the one I showed in the generation of component exchanges, generation of interfaces, or the transition from system to subsystem. And of course, it also consists of tons of little things that matter in the everyday life of engineers, and that can be as simple as copying the layout of a diagram and reusing this layout in another diagram. So the next demo is about complexity management, and it is related to functional analysis, the specific way Capella manages functional analysis. So I'm once again going to Capella. I'm going to close this model here and open another model. And I have three things to show. The first one, and I'm going to use this physical architecture to do that, is just to illustrate how we can do top-down functional analysis. So basically what would happen in a normal use case, in a top-down use case, is that you would create a function, create a second function, and then a functional exchange between them. So this function is going to be f1, this one f2, and at some point you realize that this function is too big, so you create two additional functions here, so 1, 2, and in Capella, defining a function means, I don't need this one, means you just drag and drop one part from the outer function to the child function. And this one is f21, and this one f22. And then you can add an internal refinement here. So basically, we don't have in Capella ports that are defined on intermediate functions, and we don't have delegation. And only leaf functions are allocated to components. And I could do the exact same work in F1. And I can now decide that in this view, even though F21 and F22 are useful and exist, in this view, I just don't want to see them. And then when I refresh my diagram, the tool automatically displays the exchanges between the parent functions based on what exists between the child functions. And I'm going to give another even stronger illustration of that right now. So quite often when we perform reverse engineering, we read like specification documents of our subsystems. We end up, or we use sequence diagrams, and we end up with tons of functions that are in a flat organization that are, and we don't have a good structuring of these functions. So what we can do with Capella is do this afterwards. So I'm talking here about a bottom-up approach. So I can take this, take all these functions, move them inside this box, then create another box here where I'm going to take all these functions. Okay, and I'm going to do the same for the last one here under. And what I want to do is I select them all and I move them here. So right now what I did is I have group 1, which is a function, group 2, which is another function, and group 3, another function. If I check my functional tree, which is here, my functional breakdown, I can see now that my functions are actually in a tree organization. So once I've done that, I can create a new data flow diagram where I'm, for example, interested only in the high-level functions. So I'm going to select group 1, group 2, and group 3. And when I do that, I can try to optimize the layout. Up, and then here, and then just a little bit here. Now I have a high-level synthesis of what we had on this diagram. So by doing nothing but grouping functions, I have a high-level view of these functions. And if I add a new functional exchange, for example, from Z to P, and I'm going to call it ZP, this functional exchange automatically appears on this view. I don't have to maintain the diagrams that are related to the intermediate views. They are always computed. So this is really useful, and that really helped our engineers cope with the complexity of the system they have to develop. But there's an issue with that, is that we bring in these high-level views all the little interactions between the low-level functions. So to cope with this issue, we came up with what we call categories. And categories are a way to annotate functional exchanges, to tag them, and then to propose graphical simplification based on these tags. So for example, these exchanges here between group 3 and group 1, I'm going to create a new category and say that this is configuration data, all of them. And then between group 1 and group 2, I'm going to say that these two ones and this one are actually commands. I could add several categories to the same functional exchange. And then when I come on this view or any other, I can switch the representation in this view between the atomic representation of functional exchanges or a category-based one. So now if I display commands and configuration data, I have a much simpler view, and I know that between group 3 and group 1, I have a whole bunch of functional exchanges and there are configuration data. Between group 1 and group 2, I have a whole bunch of functional exchanges, there are commands, but in the other direction, I have only one single atomic functional exchange and it's not part of a category. So using this automatic computation plus the categories, it is really easy in Capella to build simplified views of models. And then to finish this webinar, I'm going to do just a last demonstration about a topic which is pretty similar. So I have an architecture, a logical architecture, where I have several components. So my system, LC1, LC2, and some functions that are allocated to these components. And the functional tree is actually this one. So F1 is made of F11, F12, and so on. And all the leaf functions are allocated to components. The parent functions are not. Now, if I create a component, another architecture diagram where I don't see the internals of LC2, I am still able to display in LC2 the two functions that are actually allocated to the subcomponents of LC2. But because they are not directly allocated to LC2 but to subcomponents, their border is a dashed line. I could also not show F like these two ones, but I could directly show F F122 because all the children of F122 are allocated to children of LC2. So I'm just gonna come back to what I did previously. So we have a lot of flexibility in what we want to show in a specific diagram. And then between, I'm going to, we have F11, F122, 21, and then I have this. So now I have, again, at almost no cost, a simplified view of this architecture. And I can go one step further. I guess you understood the global idea. I don't even see my components anymore, but I can still visualize the functions between them and at any level. And in this case, I'm gonna show just F11 and F12. So depending on what I want to show, it might be more interesting for me to just show the simplification or show the exact detail of my architecture. The important thing is that if ever one subfunction of F11 is allocated to another component, then it will automatically disappear from this view because it is all computed. So this is the end of this webinar, trying to summarize some of the key differences between Capella and the other MBSE solution that already exist. We are available through multiple channels, the website, description group on LinkedIn, email, forums, and so on. Thank you very much for your attention.